Now what we actually did is we actually established a definition of a tangent line with slope m. What we said that if f is defined on an open interval containing a, we didn't use this terminology earlier, but that's basically what this amounted to. So now I'm bringing in the formal, a little bit more formal terminology. And if this limit equals m exists, if this limit exists, then the line passing through this known point, a f of a, that has this slope m, which we calculate from this limit, it's a tangent line to the graph of f at the point a f of a. Now, the only problem with this is this definition does not cover the possibility of a vertical tangent line. So let's just say that I have a curve that looks like this. Now, right away you go say, that is not a function. You're correct. It would violate the vertical line rule, so or vertical line test. But see, at this point here, because we will deal with this type of stuff a little bit later, this tangent is actually vertical. And this definition doesn't cover this simply because it talks about it existing, the limit existing. And we know if we have a limit, let's say the limit as x approaches a of f of x minus f of a over x minus a, if this limit, there we go, is equal to plus or minus infinity, we say that the limit does not exist. That's because the limit has to go to L, a real number. Where here we clearly said if this limit does exist. So if we get a situation where the limit does not exist because it goes to plus or minus infinity, what this is really telling you is that the tangent is in fact vertical. And there are some functions, this is not a function like I said earlier, but there are some functions, I'll show you one or two a little bit later, that we do have a point where the tangent line is in fact vertical, and if we use this limit definition, we'll end up going to positive infinity. And all that's telling you, like I said, is that the tangent at that point is in fact vertical. Now, this tangent line that we said earlier, I'm going to write it again here. We said the limit as x approaches a of f of x minus f of a over x minus a. This has several different representations. This is just one. This is yet another. A plus h minus f of a over h. Because you see, as h goes to 0, I get f of a minus f of a. Same thing here, f of a minus f of a. As h goes to 0, I get 0. Well, as x goes to a, I get a minus a, which is 0. These two are equivalent. Another very common one, and you'll see me use it more than once, is this slope of the tangent line is also equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. All of these are equivalent. See if I do this very quickly here. Have some curve, have this point. This would be a secant line. And over here would be x. And this distance here would be x plus delta x. I'm sorry, this point would be x plus delta x, with this distance being delta x. This would represent this particular notation. Now I could quickly make a quick change here. What if I called this a and this a plus h, and then this distance is now h? See, I just described the exact same thing, same diagram, exact same phenomenon, but I just described it using this notation. These are probably the three most common notation that you're going to see. So next, let's take a look at a couple of examples.